All right. So, this is active filter design, lecture 33. In the last class, we looked at various issues regarding the differential pair, and then we said that the differential pair is nonlinear. Then we also said that we also discussed how one might improve the output impedance of the PMOS current sources by cascoding. We also saw that noise of the cascode device is not an issue. So, the only penalty you pay when you put a cascode is the necessity for increased headroom, right, because you now have to drop a delta V across the lower transistor as well as across the upper transistor. And of course, there is room for optimization in the sense that now one might argue that instead of choosing delta V for both transistors, perhaps I would increase the size of the transistors and use a smaller delta V so that it can fit in the same headroom as before, right. But that has a problem with noise, because the transconductance of the lower device is what? If delta V is the overdrive, what is the transconductance of the lower device, Sailaditya? If the overdrive of a device is delta V, what is the transconductance if it is carrying a current I? It is not I by delta, it is 2I by delta V. So, any attempt to reduce the headroom by increasing delta V is accompanied by an increase in GM, which is equivalent to an increase in noise, because the noise is 8 kT by 3 times GM, ampere square per hertz. Is this clear? So, this is a constant problem with all low voltage designs, because the amount of headroom you can spare across a device is limited, and because there will be many hangers on apart from the main device which is doing the job. These hangers on will have much higher transconductance than in a higher voltage design, because by necessity you can't waste all the headroom on these bias devices. Now, if the delta V becomes smaller, the transconductance becomes larger, thereby causing the noise to become larger. All these are extraneous bias devices which are not doing any signal processing, which means that the excess noise factors of circuits designed in low voltage processes are typically higher. Okay. All right. So, let us continue from here. So, we would like to see what the problems are with the differential pair, right, as used as a transconductor. We already saw what the good things were. The good things were there are no extra nodes inside. So, in principle it is capable of very, very high frequency operation, right, and this has been demonstrated by several people, right. So, let us say you want in a given technology you want to really build a very, very high frequency active filter, okay. You find that using a differential pair is the best bet, simply because there are no extra nodes at all, right. Every node has an integrating capacitor, correct, because there are no extra nodes inside. When you build a filter with differential pairs, the input of the transconductor is a place where an integrated capacitor is going to ground, which means that the input capacitance of the transconductor can be absorbed into the integrating capacitor. Similarly, the output parasitic capacitance of the transconductor can also be absorbed into the integrating capacitor, and therefore you have what do you call potential for very high frequency operation, right. Unfortunately, the drawback is what are the problems with the differential pair? Yogesh? Okay, but beyond that, is there a more fundamental thing? What is the linear range of the differential pair is limited, okay. So, that is the biggest problem with the differential pair. Now, there are several techniques one can use to fix this problem, right. Every technique has got some problem or the other. So, when you try to fix something, something else becomes a problem, in which case you either live with it or figure out something else which solves that problem and brings in another set of problems. and this is why you have a whole bunch of publications in the area of voltage to current conversion. So let me quickly go through a catalog of linear transconductors. The simplest thing one can think of is to simply do this. Okay, and the idea for this, if we started off with the differential pair, we said that the current in a differential pair I is whatever mu n C ox W by L times Vd times delta V1 plus delta V2 by 2, right, where delta V1 and delta V2 were the overdrives of the two devices, okay, in the differential pair. And we said as Vd increases, even though the difference between the overdrives is equal to 2 Vd, the sum of the overdrives is not a constant, okay, and the sum of the overdrives, does it increase or decrease as Vd increases? The sum of the overdrives up or down? It decreases with Vd, okay, all right, and the only reason for nonlinearity is the variation of the delta V1 plus delta V2. If you look into the expression, can somebody tell me what expression we had in the differential pair? I is proportional to delta to Vd, which is delta V1 minus delta V2, okay, and delta V1 plus delta V2, and this is now what? Come on people, you don't know, why don't you at least look it up and tell me? 2 I naught by mu n C ox W by L minus Vd square, okay. Okay, so we see that if I was directly proportional to only Vd and this component was a constant, correct? If the sum of the overdrives was a constant, then the V to I conversion is perfectly linear. The reason why it's non-linear is because of this character, okay. So in other words, one could say that if somehow delta V1 plus delta V2 was maintained to be a constant by virtue of circuit topology, then it would be a perfectly linear V to I converter. And delta V1 plus delta V2, I mean, why is this constraint coming? Why is the sum of the overdrives not a constant in a differential pair? That's because the sum of overdrives is not a constant, because the sum of the currents is a constant. You understand? Okay. Now, if you want the sum of the overdrives to be a constant, obviously it means that the sum of the currents is no longer constant. And if you simply look at this guy where we remove the tail current source, in other words, there is no tail current source at all, right? This is back to two common source amplifiers operated separately. So what is I1? Mu n C ox W by L times VCM minus VT plus VD the whole square by 2, and I2 is nothing but mu n C ox by 2 W by L into VCM minus VT minus VD whole square, all right, which means I1 minus I2, which is the so called 2I, is nothing but What is it? VCM minus VT, okay, times 2, so this goes away, times VCM, sorry, VT. Does this make sense? All right. So as you can see, the current is directly proportional to Vd, which makes it in principle a perfectly linear voltage to current conversion. So what do you think are the drawbacks with this? Pardon? Yes, okay. The proportionality constant depends on VCM, so what? I can say that for any transconductor, right? If the transistor parameters change, things will change. What is the most serious problem with this? Please note that while the differential current is perfectly linear, the common mode current is what? Or rather, what is the common mode rejection ratio? The common mode gain is the same as the differential mode gain, right? So so in other words, if VCM changes by a delta V, right, both I1 and I2 will change by GM times delta V, where GM is the same transconductance you get for the differential half circuit. In other words, the differential mode gain and the common mode gain are the same. Why is this a problem? So this is a problem because you now need to have a very strong common mode feedback loop. Okay. In other words, you must make sure that the common mode gain of the transconductor is very small, such that when you put this in a gyrator, you must make sure that the gyrator doesn't oscillate for common mode signals. Okay. You understand? So there is a lot to be said for this current source. Okay, though it may not be immediately apparent, right? This current source got many problems as far as linearity is concerned, but if you are not careful with this, you will almost always end up with the gyrator. I mean, the transconductor may look fine, but the gyrator will oscillate for the gyrator will oscillate in the common mode because of the positive feedback. Okay. So there are several variants of this which I will not discuss. I mean, it's obviously impossible to go on discussing all possible transconductors. Okay. So I will take some representative examples. We will take a next improvement where the linearity is increased, right, and we don't compromise on the common mode rejection, and the inspiration for that comes from the basic electronics class, where we said we are interested in making, I mean, one thing you can see is that in all these cases in the differential pair, for example, the linearity is limited because of device properties, right? We are all using square law and all sorts of stuff, and the device is not particularly linear, which is why that's ending up with causing nonlinearity. Now, if we somehow made a voltage to current converter which didn't depend on the device, whose transconductance didn't depend on the device but depended on, for example, a passive resistor, which by definition is linear, then the transconductance is independent of the device, which means that it should in principle be much more linear. You understand? So, what is the simplest single transistor voltage controlled current source you know, where there is the device transconductance is largely unimportant as long as it's very high? Source degeneration. So, this is the incremental equivalent of the common source amplifier with feedback. This is a feedback based voltage to current converter. Okay. Please note this is an incremental equivalent. This is not the complete circuit. So, what is the exact expression for the transconductance? The incremental current I is nothing but 1 by R times GMR by 1 plus GMR times VD. Alright. So, if GMR is much larger than 1, then I is approximately VD by R. Okay. So, if GMR is much larger than 1, if I yank this by some amount by VD, what happens to this voltage? It also goes up by approximately the same amount. If this goes up by VD, what happens to this current? This is VD by R, which is what comes out of the drain. Okay. So, please note that this only works when GMR is much larger than 1. Okay. All right. So, this is the half circuit for differential mode signals. Now, you want to make it, you want to have the real complete circuit whose half circuit differential mode equivalent looks like this. Okay. So, what do you think, what all do you think you can do? Okay. So, if one way of making a real circuit, this is VCM plus VD, VCM minus VD, alright. This is R, and sure enough this gives you some quiescent current. What would be the quiescent current? VCM minus VGS by R, and what is VGS? Okay, what is the quiescent value voltage here, people? Come on. Yeah, I know it's I naught R, but in terms of the transistor parameters, what is it? It's VCM minus VT minus delta V. Okay, very good. That's this voltage. Okay, so the quiescent current will be I naught, which is this divided by R, and the incremental transconductance, rather the incremental current will be small Vd times the transconductance, which will be approximately 1 by R, provided GMR is much larger than 1. A small piece of information. To figure out whether GMR is much larger than 1 or not, one could of course run an operating point and find the transconductance of the device and compute GMR. A simpler, or rather an equivalent way which gives you the same information without running a small signal analysis is to just look at the quiescent operating point, and if this is the overdrive of this transistor is delta V, correct? So, what is the transconductance? 2I by delta V, and this times R must be much larger than 1. This is what GMR much larger than 1 means. You understand? So, the equivalent condition GMR much larger than 1 reads IR much larger than delta V by 2. Correct? And what is IR or I naught R basically? This voltage is I naught R. In other words, you can expect the linearity to be good if the quiescent voltage drop across the degenerating resistor. Okay, please note, for those of you not aware of this terminology, this is called degenerating resistor. Okay, how many of you have heard of this term before? Okay, so why is this called a degenerating resistor? Okay, so R introduces, I mean from earlier classes you have seen that R introduces negative feedback around the transistor. In the old days, negative feedback was called degenerative feedback and positive feedback was called regenerative feedback, which is why this is called the degenerating resistor. Alright. Okay, so if the quiescent drop across the degenerating resistor is much larger than 1/2 the overdrive, then you can be I mean that gives you the ratio of the two gives you GMR, and that should be much larger than 1. Okay, so are we done, or is there a problem with this also? I mean clearly the differential equivalent of this is that. Okay, so is this a problem, or is this I mean can we just proceed? How do I make now? If I decide to proceed with this, can somebody clearly tell me what I must do following this? What all other steps are involved before I get a circuit diagram of a full transconductor? Yes, so what will you do? Yes, Amrit, what do you think we'll do? Yeah, and what about the two loads? I mean, how are they operating? Yeah, I know, but where will you connect their gates? Yeah, so in all the discussions that follow, I am only going to discuss the basic V to I converter. The loads, right, will be current sources, cascoded if necessary, right? But the important thing to note is that there is some kind of common mode feedback arrangement which goes and tweaks the load currents to always be equal to the current being pulled down, so that the output common mode voltage is maintained at some VCM ref. Is this clear? All that is understood from, when I say this is the circuit for the V to I converter, the rest of it is all understood. Does it make sense? Okay. All right. Now, what do I think? I mean, so is this okay, or is there a problem with this, or there is no problem? Yeah. So what about the common mode gain? Same as the differential mode gain, because if I yank both the input voltages by the same amount, the incremental change in the common mode current is again approximately 1 by R times the change in the input common mode, correct? Because it's got no common mode rejection. You understand? All right. So going by prior experience, what will you do to fix it? The problem is that this node is grounded for both common mode signals as well as differential signals, whereas if you want common mode rejection, what do you want this node to be for common mode signals? It should be open, like in the differential pair. So what do you think we should do? Very good. So okay. Now the quiescent current in each side is simply how much? I naught. All right. Okay. And for common mode signals, what is the gain? Exactly. Yes, Amrit, what do you think is the common mode gain? Yes, I understand. No, please listen to my question carefully. What is the common mode gain is that question. Yes. Which is the source resistance? So, if the current source is ideal, what is the common mode gain? The common mode gain in principle is 0. In practice, of course, the current source will not have infinite output impedance, but it will be very large. So, the common mode gain will be very small. Is this clear to everybody? Okay. All right. So, what is the problem with this now? If you want linearity, what do you think? How do you think we will choose I and I naught and R? I mean, if you want to realize a very linear voltage to current conversion process, this drop must be many times the overdrive. So, what is the minimum voltage you can have here as the output common mode before these transistors get into the triode region? Let's assume that I naught R is n times delta V. What is the minimum value of the output common mode reference to keep everything here in saturation? The transistor requires delta V, the resistance requires n delta V, the tail current source requires at least a delta V. So, in principle, the minimum is n plus 2 delta V, whereas if you had just the differential pair, you needed only 2 delta V. Is this clear? All right. So, that is one thing. The next thing is, I mean, you know, these are all trade-offs. There is nothing you can do about it. If you want more transconductance, if you want a more linear conductance, you presumably got to trade it for something else, and that simply happens to be the headroom. All right. Now, what do you think happens to noise? There are, let's see, the noise due to the tail current source. What's happening? Is it of consequence or is it of no consequence? No consequence, because it splits equally and is only adding to the common mode noise. Differentially, it doesn't matter because it's the same on both x. Okay. So, as far as differential noise performance is concerned, we just will be happy to look at the differential mode equivalent. And to figure out how much noise is coming, what do? We short the input to ground and then replace every element with its noise equivalent, which I2 is the noise due to the resistor, I1 is the noise due to the transistor, okay, So, and the noise output we are interested is I out. So, the first job is to assume I1 and I2 are deterministic and find I out in terms of I1 and I2. So, how do we figure out I out in terms of I1 and I2? Yes, Animesh.
Sir, I1 will be 1 upon GM to be differential.
1 upon GM, okay.
And I1 we can split it.
Pardon?
For I1, the current source we will split it into 2 parts.
Yes.
So that will not have any necessity.
No, please don't assume that GMR is infinite. GMR is finite now. What is the transfer function from I2 to I out? The transfer function from I2 to I out will be GMR by 1 plus GMR. Why? It will see two impedances, one is R and the other one is 1 over GM2, and it will split in the ratio GMR by 1 plus GMR times I2, okay,
Plus GMR by 1 plus GMR into I1.
plus what is the transfer function from I1 to I out?
It will be 1 by 1 plus GMR.
1 by 1 plus GMR. Why? Again, we go through the same thing. You split I1 into two sources. The lower source is in parallel with I2, so the transfer function from there to the output will be GMR by 1 plus GMR in the negative direction. The other current source will have a transfer function of 1. You subtract the two, you get 1 by 1 plus GMR. Does it make sense? All right. Is this clear? So, what is S? I out. It's 1 by 1 plus GMR the whole square times SI of F, which is basically 8 KT by 3 GM plus GMR by 1 plus GMR the whole square times 4 KT by R. Okay. If GMR is much larger than 1, implies SI out is simply what? It will simply be 4 KT by and what is the GM? What is the transconductance of the transconductor? It's 1 by R is the transconductance. So, what is the excess noise factor? What is the definition of excess noise factor? Four KT eta into the transconductance, which is 1 by R, must be the actual noise which is coming out, which is 4 KT by R. So, eta is 1. Does it make sense? Okay. So, again, what do we see? We see that the noise of this transistor is largely unimportant as long as GMR is much greater than 1. You understand? Okay. So, Can you comment on the power required? Let's compare the two things we've seen so far, both of which have good common mode rejection and are therefore good candidates to realize a gyrator. If the size of these transistors is the same, what can you say about the transconductance here versus the transconductance here? Where is it more? Why? The transconductance you get here is Gm, whereas the transconductance here you get is 1 by R, and we know that 1 by R is there because GMR has been assumed to be much larger than 1, then and therefore the transconductance here is much higher. Okay. So now if you want to have the same transconductance in both, what do you think you should do? Let's say you didn't want to mess around with this guy, you wanted to, you could change stuff here. What do you think? Let's say the ratio of the transconductor, let's assume that GMR is N. So if I didn't want to mess with this guy, but only wanted to change something here to get a transconductance which is identical to what we get here, what do you think we should do? So you scale everything down by actually 1 plus GM. No, this is fine, right? It's approximately the size is basically like taking the differential pair, chopping it up into n parts. So each one of the parts will have a transconductance of Gm by n, correct? And therefore the power dissipation also goes down by a factor of n, and the transconductance becomes equal to Gm by n, which by definition we said was equal to 1 by R. So what is the bottom line therefore? If you design both to have the same Gm, then what can you say about any conclusions you can draw? So this consumes, so when you degenerate the differential pair, you are automatically setting yourself up for more participation, right? Simply because for the same transconductance you need to burn more power, and but what are you getting in return? You are getting a lot of linearity. Does it make sense? Okay, it seems a reasonable trade-off, right? So you burn more power, the filter becomes more linear. All right. Okay. So one sore point with this, even if you decide to burn power, is this headroom drop required. So any suggestions? I want to have the same differential equivalent, correct? In other words, as far as differential signals is concerned, this must be ground, correct? But as far as common mode signals are concerned, this must be an open, right? Further, if there must be no quiescent drop across, I mean the problem was the quiescent drop across these resistors, isn't it? Yes? Now I am adding a further constraint that they must be. So in other words, for differential signals it must look like this. For common mode signals it must look like this. This is a short circuit, this is an open, right? And there must be no quiescent current flowing through R. Okay. Okay, very good. See, the observation is that here this current is 2 I naught, right? Out of which I naught flows like this and I naught flows like this. If you do not want any quiescent current to flow through these resistors, you do not want quiescent current to flow through these resistors. So what do you think you could do? Pardon? Okay. So the suggestion was, why don't you, this current is I naught. Okay. So if you do not want current to flow through R, what can you do? I mean, of course you could remove this current source, correct? But then if you remove this current source, what happens? That's clearly a way of making sure that no current flows through R. So what is the problem now? No current flows through the transistor either, right? So now you want current to flow through the transistor but not through the resistor. So what do you think you could do? You can put I1, I naught here and another I naught where? Correct? You understand? Now by symmetry, I mean, of course in the incremental equivalent the current sources go away regardless of where you put them, correct? So for differential mode signals it will look like, this point will look like virtual ground, okay? For common mode signals it will look like an open circuit, okay? And there is no quiescent current flowing through the resistors. So what should this current be? I naught and this is VCM plus VD, VCM minus VD. This current will be I naught plus VD by R. This will be I naught minus VD by R. Is that clear? Alright. So what do you think? So clearly now what is the headroom required? The minimum required is 2 delta V, right? Or in other words, as far as headroom is concerned, this seems like the same as the differential. Okay. Now please note that if you had a differential pair and a degenerated differential pair with the same tail current, if I plot I versus VD for both of them, what is the maximum current I that can flow in either case? I naught. So for the differential pair, the characteristic probably looks something like this. Okay. Now for the degenerated differential pair, how will it look? Slope will be less, linearity will be much more. Eventually, if you put a very, very large VD, of course, all the current will flow through one transistor. That you can't avoid. Does this make sense? Okay. All right. Now, I mean, this is visually it's apparent that the linear range of the transconductor is increased significantly. You can go and do the maths, and find for a given transistor overdrive and GM and so on, what is the increment in linear range. That can be found quite straightforward. It's messy, but can be found in a quite straightforward manner. Okay. Pardon? Yeah, so you tell me. So one good thing that I am happy to see is that when somebody sees that we are gaining something, you expect to lose something, right? So you should always, whenever you are finding something for free, it's always good to look for some catch somewhere, right? So just like when somebody calls you up and says, hey, I want to give you a free credit card with like 2 lakhs this thing, and you have no income. You're sure that there is some catch, there got to be some catch somewhere, right? So just like that, it seems like now the headroom problem is solved. Linearity is much better, of course, more power dissipation, right? So is there a catch anywhere is the question. Now what happens to the current source noise? So as far as noise is concerned, earlier the noise of that 2 I0 current source would split equally among the 2 halves and therefore would not appear in the differential mode equivalent. Now what happens? The noise current of this current source and the noise current of this current source are completely uncorrelated, correct? Because they are happening in separate devices. Okay. So can we now say that this noise can be rejected, can be neglected because of differential operation? You cannot. So now we see a double whammy here, right? So as far as the noise is concerned, now we have, as far as differential mode is concerned, this is the equivalent. This is the noise of the resistor, which is 4 kT by R, and in parallel with this you have also the noise of the what? And what will that be? It will be of the form 8 kT by 3 times GM of which device? Of the device which is forming the tail current source. Okay. Now if you want to have roughly the same headroom for same overdrive for this transistor and this transistor, correct? What can you say would be the order of magnitude of this GM? Will be roughly the same as the noise of, that will be roughly the same transconductance as that of that device, correct? So, and what did we say, which of these 2 noise sources do you think will be much larger? GMR is much larger than 1. Why? If you want linearization to work, then you would want to choose GMR to be much larger than 1. If that is indeed the case, then which of these 2 noise sources would dominate? Which one? The noise due to the current source would dominate, right? So the output noise will be approximately how much? Output noise current will be how much? (8 kT by 3 GM). And what will be the transconductance? 1 by R. So what is the excess noise factor? 8 kT by 3 GM is 4 kT times 1 by R times excess noise factor, correct? So which means what is eta? 2 by 3 times GMR, and GMR is a large number or a small number? It's a large number, therefore this is a very noisy transconductor, correct? Because giving a very small amount of signal current which is proportional to 1 by R, but it's giving a hell of a lot of noise current, right? Okay. Now one can argue that, hey, the problem is the noise due to this current source, right? No. Yes. Okay. So in principle I can improve the noise factor of this transconductor by reducing the noise due to this current source, which is equivalent to saying reducing the transconductance of the device that be acting like the current source. But if I want a current I naught and if I want to reduce the transconductance, what does that mean? I must increase the overdrive. If I increase the overdrive, what happens to the headroom required? Decreases. Okay. So even though this looks like a fantastic improvement over the which one was that? Yeah. The more traditional thing was to do this. Even though this looks like a fantastic improvement over this at first sight, we see that the noise given by this transconductor is, the excess noise factor is 1 here, whereas there it is GMR, which could be very large. You understand? And if you want to fix the excess noise there, then delta V has to increase. If delta V increases, the headroom required also increases. You understand? Okay. So you have to be very careful when you evaluate different transconductors. Yes. Pardon?
I naught here and I naught there because of active. Even the source and the one junction.
No. Then 2I naught will have to flow through the transistor.
I naught from the left side.
Yeah, okay. So then what he's arguing is that, okay, instead of putting I naught at the source, you can make it a part of I naught at the source, and then in other words, you don't remove this completely, right? You have a part of it and then put two different current sources at the sources. I think I'll continue this in the